Across the globe, enormous factories are quietly transforming sunlight into one of the most important energy solutions of our time. Every year, gigawatts of solar power capacity roll off production lines, helping nations cut emissions and reduce reliance on fossil fuels. But behind every finished solar panel is a precise, carefully controlled manufacturing journey that turns ordinary sand into a high-tech energy device. Step inside a modern solar module factory and you'll see a blend of chemistry, robotics, and constant quality control working together at remarkable speed. India has become one of the fastest-growing solar markets in the world. With renewable energy capacity crossing major milestones and ambitious long-term targets in place, the country is racing to scale up domestic production. Meeting those goals requires more than large solar farms. It demands massive manufacturing capability. Companies like Vikram Solar are expanding rapidly, building advanced facilities designed to produce panels in huge volumes while maintaining strict performance standards. One such factory in Tamil Nadu represents how India is pushing toward energy independence and industrial self-reliance. The journey of a solar panel begins with one of the most common materials on Earth, silica sand. While sand itself is not useful for generating electricity, it contains silicon, the essential element behind most solar cells. Silicon's abundance makes solar technology more sustainable in the long run, since the raw material is widely available. To extract it, silica is heated in powerful furnaces at temperatures reaching around 2,000 degrees Celsius, combined with carbon to remove oxygen. The result is metallurgical-grade silicon, a raw but usable form of the element. This silicon still isn't pure enough for solar applications. It must undergo additional refining to remove impurities that could interfere with electrical performance. The silicon is melted again and carefully processed until it reaches a much higher level of purity. Small, precisely measured amounts of elements like boron and phosphorus are then added. These additives are critical because they control how the silicon conducts electricity, creating the positive and negative layers needed for photovoltaic action. Once prepared, the molten silicon is formed into solid blocks known as ingots. These ingots are slowly cooled to ensure a uniform crystal structure, which directly affects how efficiently the final solar cell will convert sunlight into electricity. The ingots are then sliced into ultra-thin wafers, often less than 1/4 millimeter thick. These fragile wafers are the foundation of every solar cell, and handling them requires extreme care to avoid cracks or breakage. To improve performance, each wafer undergoes surface treatment. A thin coating of silicon nitride is applied, giving the wafer its distinctive bluish color. This coating reduces reflection, ensuring more sunlight is absorbed rather than bouncing away. The surface is also textured at a microscopic level, helping trap incoming light. After that, fine lines of silver paste are added to the front and back. These lines act as electrical contacts, allowing electrons generated by sunlight to flow out of the cell. At this stage, individual solar cells are ready for inspection. In a modern factory, incoming cells are examined both by trained workers and automated systems. Any cell with visible cracks or defects is separated. While badly damaged cells cannot be used in full-sized panels, smaller intact sections may still find use in low-power devices, reducing waste. Quality control begins early because even tiny flaws can affect long-term performance. Next comes electrical testing under artificial sunlight. Powerful lamps simulate real solar conditions, allowing engineers to verify that each cell produces the expected voltage and current. Cells that pass move forward into module assembly, where dozens of cells will be combined into a single panel. This is where automation takes over in a big way. A sheet of tempered glass forms the front layer of the panel. This glass must be strong enough to withstand years of exposure to weather, heat, and mechanical stress. On top of the glass, a transparent adhesive layer known as EVA, or ethylene vinyl acetate, is applied. EVA plays a crucial role, bonding the cells to the glass while allowing light to pass through with minimal loss. Robotic arms then place solar cells onto the EVA-coated glass in a precise pattern. These robots work with incredible accuracy, positioning multiple cells at once to ensure uniform spacing and alignment. Thin metal connectors, often called fingers and bus bars, link the cells together electrically. The design of these connectors is carefully optimized. Too few, and resistance increases. Too many, and they block incoming light. Engineers constantly balance these trade-offs to maximize efficiency and durability. Once the cells are arranged and interconnected, another EVA layer is placed on top, followed by a protective backsheet. This creates a layered structure that seals the cells and wiring inside. Before the panel is permanently bonded, It undergoes a special inspection known as electroluminescence testing. When an electrical current passes through a solar cell, it emits faint light. By capturing images of this light, inspectors can spot microcracks that are invisible to the naked eye. Dark lines or patches reveal areas where the cell may fail over time. Microcracks are a major concern in solar manufacturing. Silicon is brittle, and damage can occur during almost any step, from wafer slicing to transport. Even temperature changes can stress the material. Detecting these flaws early prevents defective panels from reaching the market and ensures consistent performance in the field. After passing pre-lamination checks, the panel enters the laminator. Heat and vacuum pressure are applied, melting the EVA and bonding all layers into a single, weather-sealed unit. This process locks the cells in place and protects them from moisture, dust, and mechanical damage. Once laminated, the panel is far more robust, but testing is still far from over. Metal ribbons are attached to carry electricity from the internal cell network to the outside of the panel. An aluminum frame is then fitted around the edges. This frame adds strength, making the panel easier to handle and install while also protecting against bending and impact. It also helps the panel survive environmental stresses such as strong winds, heavy rain, or snow loads over its lifespan. Another round of electroluminescence testing follows, ensuring no new damage occurred during lamination. After that, a junction box is attached to the back of the panel using durable silicone adhesive. This small but vital component collects the electricity generated by the panel and directs it outward through cables. Inside the junction box, diodes prevent electricity from flowing backward, which could damage the panel or reduce system efficiency when sunlight levels change. The final stages focus on reliability. Panels are checked for sealing integrity to ensure they are fully weatherproof. Any weakness could allow moisture to enter, leading to corrosion or electrical failure years down the line. Once sealing is confirmed, the panel is tested one last time under simulated sunlight to verify its power output meets specifications. Only after passing all these checks is the panel approved for shipping. Facilities like Vikram Solar's plant in Tamil Nadu are more than production centers. They represent a strategic shift. By manufacturing solar panels domestically, India reduces its dependence on imports and builds local expertise. This aligns with the broader vision of creating a self-reliant energy ecosystem where advanced technology, skilled labor, and innovation are developed within the country. Modern solar factories are also preparing for the future. Artificial intelligence and machine learning systems are increasingly used to monitor production lines, analyze test data, and detect defects faster than human inspection alone. These tools help improve yields, reduce waste, and push the limits of panel efficiency. Research and development teams use factory data to experiment with next-generation cell designs and materials, ensuring continuous improvement. Behind every finished solar panel is a story of precision engineering, relentless testing, and global ambition. What starts as ordinary sand becomes a powerful tool for clean energy, capable of producing electricity for decades. As solar capacity continues to expand worldwide, factories like these will play a central role in shaping a more sustainable energy future. So the next time you see a solar panel gleaming in the sun, remember the journey it took to get there. From furnaces hotter than molten lava to robots placing cells with microscopic accuracy, it's a process driven by innovation and optimism. And with countries investing heavily in renewable energy, that optimism might just be well placed.